morning to everyone. I am Maria Colaschetti and I'm here today to describe to you the experimental campaign that was conducted in collaboration between Material and Structure Research Laboratory of the University of Bologna in Forlì and Enea Research Laboratories in Faenza and Rome. Today, after a brief introduction about composites in aeronautics and their issues related to impact behavior, I'm going to describe to you the experimental campaign and therefore specimen characteristics, all the impact tests and the compression after impact tests that were performed, the results that we obtained and the conclusion that we got. In the last 40 years, composites have seen a huge rise in their use in aeronautical field due to the possibility to have integrated structure with less joints and therefore a theoretically lower weight compared to a metallic structure. On the other hand, there are still many unknowns about composite structure, in particular related to environmental effects and impact behavior. For example, while for metal structure under fatigue loads, we know that under fatigue loads, the decrease of their residual strength is quite gradual and predictable. For a composite, it's not like that. Even if they could have higher residual strength at the beginning, due to a foreign object impact, the residual strength can drop down even under ultimate load, and therefore this could result in a catastrophic failure. Therefore, airworthiness regulation says that if you want to design a new composite structure, you have to apply the no-grow concept, and therefore for a new structure, new damage must nucleate, and if a damage is already there, it must not grow. Therefore, you have to apply really conservative approaches, like for example, even apply metal reinforcement in the door cutouts, and at the end, a composite aircraft has a weight that is comparable to a classical metal one. One of the most important issues related to composite in aeronautics is related to impacts. There are many different kinds of impacts and many different kinds of damages that these impacts could create. But the most dangerous one is that is known as very visible impact damage. This kind of damage has no evidence on the structural surface. And even if there is an evidence, the indentation is really thin and can be easily skipped during a normal visual inspection. But in the inner part of the structure, there could be delamination or other kind of damage that could influence structural property. And this kind of impact has also a lot of causes. For example, running debris on the landing field, or even maintenance and stamping tools that can fall down. But even a passenger during a boarding can hit the door surroundings with their luggages. So there is a necessity of experimental analysis, and that was the reason that moved us to this kind of research. The first step of this research was presented in the previous IGF meeting in 2015, and that experimental campaign was conducted on 2.6 mm carbon epoxy specimens with 2 different energy levels and 2 different impact locations. And we saw that even a really low energy impact on this kind of material is really effective on its compressive residual strength. And the location of the impact is really important. So we wanted to do a step forward in this direction, trying to find out which is the thickness influence on impact behavior for a carbon epoxy. We made a 5.5 mm thick carbon epoxy laminate. We cut it into 25 specimens and divided them into 5 groups. Each group was characterized by a different kind of impact, different energy and different location. The leitmotif was to still obtain barely visible impact damages, as you can see in the picture. While on the other side you can see impact location for the central impact and the near edge impacts. All the impact tests were performed by means of a modified short-wave pendulum. Each test was filmed, each video was watched in slow motion to be able to capture the real initial angle and the bounce angle in order to obtain the actual energy, the residual energy, and to be able to calculate the energy absorbed by the specimen. After the impact test, we did the non-destructive inspection test, in particular the ultrasonic test, and here you can see an example of the 7 joule near edge impact specimen where the damage is stressed in blue spot, while on the other side you can see an example of each one specimen, impacted specimen from left to right. And you can see here that the damage is stressed in red, and in particular it's really evident the specimen that was impacted near edge with 7 joule and the other one that was impacted centrally with 7 joule energy. To check which is the influence of the impact damage on compressive residual strength and therefore to perform a compression after impact test, we chose to use the combined loading compression test method due to its many advantages compared to other kind of compressive fixtures. Those are the results for the pristine material, for the 5 joule near edge impacted specimen, 7 joule, 5 joule central impact, and 7 joule central impact. And here the results are summarized. This table is referring to the present experimental campaign, and you can see that difference between all the mean values of the groups is not really high. You can see that there is a slight reduction in compressive residual strength for the near edge impacted specimen. While we saw in the previous campaign with a thinner specimen, with a thinner material, just 2.6 millimeter thick, we saw that the difference was really huge. All the impacted specimen had a reduction in compressive residual strength, and the location was really important because it was really higher, that reduction. If we compare the 5 joule near edge impacted specimen from both the experimental campaign, we can see this clearly, because for the thin material, there was a reduction of around 50%, while for the thicker one, for a 5.5 millimeter carbon epoxy, the reduction is around 5%. Therefore, there is not a clear evidence of the impact influence on the compressive residual strength of this kind of thick material. Therefore, what we have seen is that for a thin material, 2.6 millimeter thick carbon epoxy, even a really low energy impact is really important and really effective on the compression after impact, in the compressive residual strength. Sorry. And the location is really important for that kind of thickness, but when you have a thick specimen, in this case a 5.5 millimeter thick material, this influence is not so clear, and you have just a slight reduction for near edge impacted specimen. But there are two things that we can underline from this experimental campaign. First, during the compressive tests, we saw that the near edge impacted specimen filled easily, or more easily than the others, in this gauge section, therefore in the section where the damage was, while the other kind of impact, the central impact impacted specimen, didn't behave in that way. Therefore, even if the influence on the compressive residual strength is light, the near edge impact is still creating a weak spot in the material, and therefore a trigger for the damage. That could be, and therefore the near edge impact is still more dangerous than a central one. And second, we saw that there is an energy threshold for impact, or for low impact behavior for carbon epoxy. And under this pressure, even if the impact creates a damage, this damage doesn't really have effects on the compressive residual strength of the material. But the next step could be to test higher energy with this kind of thickness, or even different thicknesses, in order to be able to correlate material thickness with this energy threshold.